All right, so in part one, we're doing trig integrals. One type of trig integral involves powers of sines and cosines. So I would write them as sine raised to the m power times cosine raised to the n power. And there were two cases. It's either or both m and n are odd. That's the easy case. You make a Udu integral out of it. If both m and n are even, then you use the power reduction formula. You'll make a Udu integral by pulling out a factor of one of the odd power trig functions, and that becomes your du. Then you use the Pythagorean identity to write the rest of the integral in terms of the other trig function. So you're going to use some version of sine squared of x is 1 minus cosine squared of x, or cosine squared of x is 1 minus sine squared of x, to write the rest of the integral in terms of the opposite trig function. If both m and n are even, then you use the power reduction formulas. That sine squared of x is 1 minus the cosine of 2x over 2. Cosine squared of x is 1 plus the cosine of 2x all over 2. Once you use the power reduction formulas, then hopefully you do a little algebra part and get integrals that you know how to do. Or you keep using this over and over until you do. Let's do one of each type. Let's integrate sine cube of x times the cosine squared of x dx. So I see that big old odd power on the sine. That means I'm going to take one factor out of it and stick it next to the dx term. So I'm going to write sine cubed is sine squared times sine, like this. So I'm setting that term up to be the du. All the other things need to be in terms of cosine. So we're going to substitute this out using sine squared is 1 minus cosine squared. And our integral becomes 1 minus cosine squared times cosine squared times the sine of x dx. And then we can do a Udu substitution. Just take u to be the cosine. And du is going to be minus the sine of x dx. So I'm going to put a minus with the du, and I'll put the minus sign way out front. And our integral becomes minus the integral of 1 minus u squared times u squared times du. Got all that? Then multiply it out, and then you can integrate term by term. So we multiply it out and get a u squared minus u to the fourth with the minus sign way out front. Or you can change the order of it and put that minus sign inside as a u to the fourth minus u squared. Does that bother you anyway? That minus sign in? Go that far back. Except for that minus sign out front, I pulled in. And so when you integrate that, let's do it all in here. We get a u to the fifth over 5 minus u cubed over 3. For each u was the cosine of x. So I have the cosine to the fifth of x over 5 minus the cosine cubed x over 3 plus c. So if any one of these or both of them are odd, take an odd factor out, the remaining factor's even, substitute it out with Pythagorean identity, and you've got a Udu integral. Works every single time. Except for when the powers on the sines and cosines are even. So let me change the 3 to a 4. We'll integrate sine to the fourth times cosine squared. So I don't have the opportunity to make it instantly a Udu integral. If I take one of the cosines out, then I have a cosine left, and I won't be able to write cosine to the first power in terms of sines. I need an even power to use the Pythagorean identity. So instead, I'm going to think of this as being a sine squared squared and where I have the sine squared, I'm going to put in 1 minus cosine of 2x over 2. And where I have the cosine squared, I put in a 1 plus cosine 2x over 2. Replace them both. So the first one would be squared. And the second one is just 1 plus cosine 2x over 2. But now we have to do the algebra. We have to expand that so that I have the sum of terms. So I've got to square that first batch, and then I've got to multiply it by the next one. Let me collect the halves first. This 2 squared is going to give me a 4, times that's going to give me an 8. So I'm going to put a 1/8 out front, and then I'm going to square this guy. 1 minus the cosine 2x all squared gives me 3 terms. 1 minus 2 cosine of 2x, and then plus the cosine squared of 2x. Then I'll have to multiply that through by 1 plus the cosine of 2x. So the first thing I'm going to do is multiply everything by 1. Then I'm going to multiply everything by the positive cosine of 2x. So we're going to get 6 terms in here. multiply by 1, I get 1 minus 2 cosine of 2x plus the cosine squared of 2x. Now I'm going to multiply each of those terms by the cosine of 2x. So cosine of 2x times 1. I'm going to just put it underneath this one and I'll compile them next time. Cosine of 2x times that gives me negative 2 cosine squared of 2x. And then I'm going to have plus cosine cubed of 2x. Now let's put our like terms together. I'm going to have 1 minus the cosine of 2x minus the cosine squared of 2x plus the cosine cubed of 2x. The first three are going to be relatively easy. We need to first get rid of the 2x. Let's go ahead and do a Udu substitution. Let's take u to be 2x, and then the du is going to be 2 times dx. So I'm going to get yet another factor of a half out there. Let's rewrite that integral in terms of u. Take this half out here, and I'll get 1 over 16. 1 minus the cosine of u minus the cosine squared of u plus the cosine cubed of u. We're going to hang on to this one. We'll do that separately, but I can do the first three right away. We're integrating with respect to u. So I'll get u minus the sine of u, and then remember our formula for the cosine squared. You have the integral of cosine squared still in your head? You're looking for it. So let's do that. I'm going to have 1 over 16 u minus the sine of u minus, so in here I'll have u over 2 plus the sine of 2u over 4. Plus whatever I get by integrating the cosine cube. Boardroom I've got left here. Don't have any boardroom left. So we're going to integrate the cosine cubed up over here. Any thoughts? Take the cosine out. It's the odd power rule. Take one of the cosines out as the du. Actually, we're going to have to change variables. So I'm going to have a cosine squared of u times the cosine of u du. Use the Pythagorean substitution. The cosine squared is 1 minus sine squared. Now we're going to do a substitution, but we already used a u, so let's grab another letter in our alphabet. I'm going to use t. I'm going to take t to be the sine of u, so that dt is the cosine of u du. And so we're integrating 1 minus t squared times dt. And we'll get t minus t cubed over 3, where each t is a sine of u. And so where I have the little asterisk down there, I'm now going to stick that in. This integral right here becomes 1/16 times u minus the sine of u. I'm going to distribute the minus sign here, minus u/2 minus the sine of 2u/4. And now replace that little asterisk with the sine of u minus the sine cubed of u/3. And then lastly, put in 2x where each u is. There is some simplifying we can do. This sine of u adds out with that one. And I can combine this u minus u/2 and get a positive u/2. So let's do that. And at the same time, each u was 2x. U minus u/2 is u/2, so 2x/2. Gone, gone. Sine of 2x. What's that one's gone? Sorry, this one. Minus sine of 4x/4. So that one took care of that one, and is that. That one and that one are gone. That one's here. Now minus sine cubed of 2x/3. Okay. So when you've got even powers, you've got to do a lot of algebra. Okay. All that, anybody? Anybody? Okay, let's do tangents and secants. That wasn't as cut and dry as this is. When there are two things to remember, make a UDU integral if any of the powers are odd, do a power reduction integral if both of the powers are even. So next, to integrate powers of tangents. We have to remember that the derivative of a tangent is a secant squared, and the derivative of a secant is secant tangent. So since the derivative of a tangent is secant squared, if the power on secant is even, pull out a secant squared. That's going to go with the du term. So you have to write the rest of the integral in terms of tangents. So you'll have some even powers of secants left. Then you replace the even secants that remain with tangents using the fact that, what was it? I always forget it. Sine squared plus cosine squared is 1. Divide by cosine squared says that tangent squared plus 1 is secant squared. If both powers are odd, then we pull out the secant tangent. actually, we don't care what the power is on the secant. That could be even or odd. So let's just say if the tangent power is odd. If the tangent power is odd, pull out a secant tangent and then replace the tangents that remain with tangent squared is equal to secant squared x minus 1. Then in either case, once you do that, you've got a Udu integral. So the case that I'm leaving out is if the tangent power is even and the secant power is odd, then we've got this. If this is even and that's odd, then sometimes we end up doing integration by parts. Okay, so but let's do the first two cases, and then we'll see if we can stumble into the other ones. Did we do any of these last time? Okay. So how about we just do a secant of 4. Whether there's tangents in the integral or not, once you see the even power of the secant, you pull out a secant squared. This one's going to act as the du term, so the stuff to the left of that has to be written in terms of tangents. And secant squared is tangent squared plus 1. Now you do a Udu substitution where you take U to be tangent. And the du is the secant squared. We're just integrating u squared plus 1 times du. So u cubed over 3 plus u. And h2 is a tangent. Here, having the even power on the secant made this an easy problem. Having an odd power on tangent makes an easy problem. If there's a secant present. If there's not a secant present, then it's not so great. We could still do it. So let me put some secants in here and an odd power on the tangent. How about we do, what did you say we did last time? Did we do tangent cube, secant cube? Let's do that one. So the fact that this is not even keeps me from pulling out a secant squared. But the fact that this odd allows me to pull out the secant tangent, leaving me a tangent squared behind. I got to pull out a secant out of here. Let's think of what could be my du. you can get that figured out, and everything else fits the Pythagorean identity, then you're good. So if that's my du, then u has to be a secant. U has to be secant, we need to get tangent squared out of there. And so we do. Tangent squared is secant squared minus 1. So as soon as you've taken that step, you can go ahead and do the Udu substitution. Use secant of x, du, the secant of x, tangent of x, dx. And so we're integrating u squared minus 1 times u squared times du. Once we multiply that out, we just integrate term by term. I'm integrating u to the 4th minus u squared du. We get a u to the 5th over 5 minus u cubed over 3. And each u is a secant. So our answer is secant to the 5th over 5 minus secant cubed over 3. Let's look at one where the tangent power is odd and the secant power is odd. Already did that. How about when the tangent power is even and the secant power is odd? That's one of these lists. Because that doesn't fit either one of these. This is part of this. And we put a secant in there. Okay, now I gotta just kind of make it up as I go. It doesn't tell me over here what to do. I'm start counting. And keep my cool here. I'm like the all-knowing one. Ah, okay. That's my first step. Who knows if it works, but I see a tangent squared that'll at least allow me to get a secant squared in this integral. Okay, so I'm going to replace this tangent squared with secant squared of x minus 1. And if I distribute that tangent through there, I at least have an integral that I know how to do. Can you do that first integral? u squared du integral. So we got half of it done. Now we're worry about this one. So for this integral, we take u to be tangent. Du is secant squared. And this first integral is just the u squared du. So we get a u cubed over 3. Let me skip a step and just write that as tangent cubed x over 3. All right, we're ready for partial credit. Now I got to figure out how to do this one. Okay, I can integrate tangent squared because I know tangent squared is secant squared minus 1. You know the integral of secant squared? That's a tangent. I'll help you out. The integral of 1 is going to be x. So making this substitution gives me this integral is just a tangent of x. And then minus the x. So plus x plus c. So you got to remember that you know how to integrate secant squared. Get rid of the tangent squared, put the secant squared minus 1 in there. So they're not all terribly hard. What would have made this messier is if I put a tangent to the 4th times the secant in there. And then that's much messier. Yeah, can do it. But you lose interest quickly. And I'm here to pique your interest, not to scare you away. And I've only scared a few people away. Okay, the other cases involve cosecants and cotangents. So you just have to see if you have a UDU integral. And the Pythagorean identity for cosecants and cotangents. Let's see, I know sine squared plus cosine squared is 1. Cotangent is a cosine squared over a sine squared. So the Pythagorean identity that we might need is 1 plus the cotangent squared is equal to the cosecant squared. And then if u is a cotangent, du has a cosecant squared in it, minus. If u is a cosecant, then du has a cosecant cotangent with a minus. And you follow almost the same pattern. You look at what's going on here and what you can pull out. So I bet if I just change this to cotangent and that to cosecant, all of these steps are the same. So I'll hide those steps so you can't see them, and then do that. So we can interpret it this way. If the power on the cosecant is even, pull out a cosecant squared. If the cotangent power is odd, pull out a cosecant cotangent. And it should work the same way. So I got the odd power on the cotangent. I'm going to pull out a cosecant cotangent. So I'm setting up my du. That comes from taking the derivative of a cosecant. So I need everything else in the integral to have nothing but cosecants in it. I've got an even power on a cotangent. Let's replace cotangent squared with cosecant squared minus 1. Again, that's going to be a du. So I got to take u to be the cosecant. Except for that spits out a minus sign. So I'll go ahead and move the minus sign over to the du. And so we're going to have minus the integral of u squared minus 1 times u squared times du, blah, blah, blah. The rest is the same. Okay? So there's really no difference in our strategies if I slip out a cosecant for a secant and a cotangent for a tangent. Okay? So how do you think you'd integrate a cotangent to the 4? Well, you write it as a cotangent squared to cotangent squared. And then you leave your cotangent squared and replace your cotangent squared with cosecant squared minus 1. Right? Everything is identical. Same game plan. Okay. That was integrating trig functions part of this section. The other part was getting rid of pesky radical signs. If you have an integral that's not quite one of your inverse trig integrals, something's amiss, then you've got to think of something else to do. So here are some integrals that you already know how to do. You can do each of these. I might have to whack you upside the head a few times. You know these two. You don't know this one. If it had a minus sign in there, you do know it. That's under the you know these. That minus sign under the between the 4 and the x squared. You know that one. You know this one. But you don't know this one. And you don't know this one. See the slight differences? You're probably saying, I don't know any of those know that one. You know this one or any version of this one because if the degree on top is 1 more than the degree on the bottom, that's a Udu integral. So if I put x here, that's a Udu integral. That's an inverse tangent integral. That's an inverse sine. That's an inverse secant. And if they're off by just a little bit, they're not Udu integrals, they're not inverse tangents, they're not inverse secants, then we've got to do something to get the square root signs out of there. And so we have the 3 Pythagorean identities that help us get the square root signs out of there. I know 1 minus sine squared is a cosine squared. And so if I have something that looks like a squared minus x squared, then I'm going to take x to be a sine of theta. I need a different variable. But don't forget the dx. That swap would make this look like a squared sine squared. So I can factor out the a squared and have a 1 minus sine squared. And 1 minus sine squared is cosine squared. So I could replace the difference of 2 terms with a single trig function. Then I can take the square root of it. If I have a squared plus x squared, I know that secant squared, well, I know that tangent squared plus 1 is equal to secant squared. And so if I have 2 things added here, then I take x to be a tangent of theta. Of course, then I need the dx. But anyway, this term then would be a squared tangent squared. with the common factor of a squared, I pull that out. 1 plus tangent squared becomes secant squared. And then if my variable was in front of the minus sign, then I go with the secant, because I know secant squared minus 1 is a tangent squared. So here I would take x to be a secant of theta, and then dx is a secant theta tan theta d theta. Then we can do every one of those integrals. And let's just go ahead and do one of them. Let's just do that first one over there. The 1 over the square root of 4 plus x squared. So that's this case. Number squared plus a variable squared. The order doesn't matter when it's plus. So here my a squared is 4. So a is going to be 2. We're going to replace x with 2 times tangent of theta. Now to replace the dx, we take the derivative there. So we get 2 times the secant squared of theta. Theta. Then we get a trig integral that hopefully we know how to do. So let's put that in there. We have 1 over 4 plus square the 2 tangent, right? X squared is going to be 4 tangent squared. The dx is 2 secant squared theta d theta. So can you kind of look ahead? What's going to happen? I'm working under the radical sign. Got a common factor of 4. I'm going to pull the 4 out. And my Pythagorean identity was that tangent squared x plus 1 is secant squared of x. Tangent squared theta plus 1 is secant squared of theta. So this first term is going to become 4 secant squared of theta under the radical sign. I'm going to slide that over here. Like that. But I've gotten rid of the difference or the sum. Now I can take the square root because I have a product. That's perfect square. The square root of 4 is going to give me 2. The square of secant square is going to give me a secant down there. Or square root signs. In fact, I only have a secant of theta to integrate. That's when I asked you to learn. Did anybody learn it? It's not to a natural log. I have ways of making you learn this. Involves a counter product. Secant theta plus tangent of theta. Okay, we're not done. We've got to replace each of the secants and tangents. We're going to get back to our original variable. So from up here, if I solve that for the tangent of theta, the tangent of theta is x divided by 2. So I'm going to replace that with x over 2. If I know the tangent of theta, then I know all 6 trig functions of theta. I can draw a picture to help me remember it. Here's angle theta. Tangent is the opposite over the adjacent. So I can put the x opposite that angle and 2 adjacent to that angle. Secant of theta involves hypotenuse over adjacent. So can you figure out the size of the hypotenuse? Hypotenuse squared is x squared plus 2 squared, so hypotenuse is x squared plus 4 under the square root sign. The third side should always mimic that. And so now I know the secant of theta, hypotenuse over adjacent. So our final answer is natural log of the square root of x squared plus 4 over 2, tangent of theta plus x over 2 plus c. Okay, yes, sir.
Where did we get the 2 secant squared?
From the derivative. You need something to go in for the dx as well. Don't ever forget that, otherwise you have to figure it out how. Don't forget your dx. It doesn't automatically turn into d theta, it turns into a trig function times d theta. Okay? If we move to another room, why? This is a perfectly good room. I don't know if there's anybody coming in here after us. Is there? Have you ever noticed if anybody comes in this room after us? Let me peek out the door. No, maybe we'll stay, huh? They go in after us. There's somebody out there. Walk around for a little bit, see if anybody shows up. If not, we'll just stay here. Back here, we'll do this just in- Let me see, I had some homework papers here. Maybe I can get those back while everybody's waiting for somebody to take us out of this room. So if you can remember the stuff in the little red squiggly lines, you will have happy, healthy lives. Those substitutions will usually allow you to get rid of the radical sign using the Pythagorean identity over here, and should give you a trig integral that you know how to do. So let's do the one that almost looks like the inverse secant, except for the x and the number were in the wrong spots. Four minus x squared, where x squared minus 4, then we could do an inverse secant integral. If that x is on the bottom, was up on the top, then we have a Udu integral. It's not quite either one of those two known integrals. The x behind the minus sign makes me think of this Pythagorean identity. 1 minus sine squared is cosine squared. So I'm going to choose some version of the sign to be this x. In order to have a common factor of 4 after I square it, I'm going to take x to be 2 times the sine of theta. So each of these x's down here will be 2 sine of theta. Now we get a dx term by taking the derivative here. Now let's substitute it in and watch the magic happen. So this x becomes 2 sine of theta. Under the radical sign, I'm going to have 4 minus 2 sine of theta squared. It's going to give me 4 sine squared theta. Then the dx that was here becomes 2 cosine theta d theta. So I'll put the 2 cosine theta on top, then the d theta here. See where everything comes from? Ask me if you don't follow that. So now I'm looking underneath the radical sign. We'll pull out a 4, just between those two terms and have 4 times 1 minus sine squared of theta. I don't want to write the whole problem down again. Let's just kind of do this scribbling. We'll pull out a 4 and have a 1 minus sine squared of theta under there. That was what I was hoping for. 1 minus sine squared is cosine squared. So in the next step, I'm going to replace that stuff underneath the radical sign with 4 times cosine squared of theta. Just bring it down here. We have 2 cosine theta on top. 2 sine theta here. Now my square root sign, then I have 4 cosine squared of theta. Making it from a difference to a product now allows me to take the square root, and square root sign is now gone, and I just have a 2 cosine theta down there. We can cancel it. 1/2 can come out front, and then we have 1 over sine of theta. What are we going to do with that? That's a cosecant. That's a cosecant. We have 1/2 the integral of the cosecant of theta. That one has a formula just like the secant did. Remember, the integral of a secant was the natural log of the secant of theta plus the tangent of theta. This one's going to have a formula that's got a natural log in it. But instead of secant of theta plus the tangent of theta, what do you think is going to be in there? So secant of theta plus the cotangent of theta. And it's going to be a minus sign out front. You have minus 1/2 natural log cosecant of theta plus the cotangent of theta. Minus sign came from the fact that the Udu substitution in generating that formula has a minus in it. That's the antiderivative. Now we need to get everything back in terms of the original variable. So let's go back to the original substitution and write this as x over 2 is equal to the sine of theta cosecant is the reciprocal of the sine, so 2 over x is the cosecant of theta. And then draw a picture to figure out what the cotangent is going to be. There's angle theta. Sine is opposite over the hypotenuse. So hypotenuse squared minus leg squared is this leg squared. So 4 minus x squared under the radical sign goes here. Again, if you do things right, it should be the radical portion of your original integrator. But now I can get the cotangent of that. The cotangent is adjacent over opposite. So it's 4 minus x squared divided by x. And we put it in here, and we should be done. Cosecant was 2 over x. Cotangent was 4 minus x squared. Okay. Yes. Because what you do with the d theta? You can't just ignore it. It is a function of x as well. That was pretty clever. I thought maybe you were onto something, but you can't just ignore this guy. So if you took the derivative here, I guess your d theta would have that in it. Cosine. Eventually get back to here, I suppose. You start doing that then. Okay. Put those two intervals as intervals that you need to remember. The interval of the secant is the natural log of the secant plus the tangent, and the cotangent is minus the natural log of the cosecant plus the cosecant. You could also know the integral of the tangent, the integral of the cotangent by themselves. The integral of the tangent. Integral of tangent is minus the natural log of the cosine. Integral of cotangent is a positive natural log of the sine. Those might poke their heads out every now and then. Like they did right here. Ready for another one? Anything you want to ask before we're reading this out? What happens in become part of this? Just the trig identity. Just carry the number in. Okay, so all this junk out. There are some algebraic manipulations that could do some of these intervals. And some of you have been turning some of them in, but skipping all the meaty steps that get you from the hard interval to the easy interval. The algebra that you guys have been skipping, as they say on the streets, is a bitch. This is easier than the part you've been skipping. This is a very similar integral to the one that we've done. In fact, they all look alike after a while. If that were an x to the first power out front of that square root side, that's an inverse secant integral. That's not an x to the first power out there, that's an x squared. So it's not quite an inverse secant integral. But I do know that secant squared minus 1 is a tangent squared. So my choice here is going to involve a secant. I need to have a common factor of 9, so I'm going to replace x with 3 times the secant of theta, so that I get a secant squared minus 1 after I factor out the 9. Okay. I need the 3 because I'm a square, I need the common factor. Then secant is secant tangent. So you get 3 secant theta, tan theta, d theta. And x squared is going to be 9 secant squared. Let's substitute that all in there. X squared is 9 secant squared of theta. Then I get it under the radical as well. And then my dx has a 3 secant theta, tan theta, d theta. So I'm going to slide that up here. Now let's just work under the radical sign, factor out that 9 so that we have a secant squared minus 1. And replace secant squared theta minus 1 with tangent squared theta. That's now under the radical sign. We rewrite it so you can see it. Again, those substitutions are set up to mimic the Pythagorean identity so that you can replace the difference with a single perfect square. Now you can take the square root of that 9 tangent squared theta and get a 3 tangent theta. I'll go ahead and put that step in so we can more accurately see what's going to cancel. Now cancel to your heart's content and tell me what you got left. 1/9 of 1 over the secant. 1/9 of 1 over the secant. Here's the 1/9. Here's the 1 over the secant. Let's mark things out with my red. You can do that. 1 over secant is cosine. This is the easiest one we've had yet. Cosine is a positive sign. So your 1/9 sine of theta. We need to get our antiderivative back in terms of the original variable. So we go back to here. Solve that for the secant of theta. We get x over 3 is the secant of theta. That describes the hypotenuse divided by the adjacent. So make the hypotenuse x, make the adjacent side 3. X squared plus leg squared is x squared. So this leg is going to be x squared minus 9 under the square root sign, and that's that. And so the sine of that angle is opposite over the hypotenuse. Opposite is the square root of x squared minus 9. The hypotenuse is x. This is the most fun you've had all day, admit it. Got that for our next one. Not a UDU integral, because if U is this, I would need the next to the first power out here. So just missed being a UDU integral. So I've seen how these trig functions can help me. The trig identity that has a plus sign in it uses a tangent. But I've got to figure out an adjustment so that I have a common factor after I make that substitution. Yes, sir. There's not a DU. Because the word's DU. What am I gonna do about that X? There's nothing to suck that up. There's the DX can't be D over 8X. So then I'm gonna put in X. Right, that's the big problem. I don't have this X in here. So not everything's a UDU substitution. It's close, it's just not there. And so if it's close but not there, these tricks tend to work. So let's see. What do you want to do about the 4x squared plus 12? Factor 4 out? We can do that. What if this wasn't divisible by 4? What if that was a 10? Let's make it a 10. Well, let's make it an odd number. Let's make it 7. Let's get factor 4. Again, I guess I have 7 fourths. Right? I can do this. And now I take the 2x. My 7 is playing the role of the a squared. And this is my variable squared. So I can say let 2x be the square root of 7 times the tangent of theta. Because after I square the 2x, I'll get 7 tan squared and I have a common factor of 7. What do you think? Then I need a dx, so take the derivative of this, we get 2 times dx is the square root of 7, derivative of tangent is a secant squared times theta. So I have to move this 2 over here. Dx is square root of 7 over 2, secant squared theta d theta. So now in for the 2x, I'm going to put this. Just to do that step right here, 2x all squared will give me a 7 tan squared theta. So I'm going to put 7 tan squared theta plus 7 under the radical sign. Then the dx becomes this thing, the square root of 7 over 2 times secant squared theta d theta. So next we manipulate that expression into the radical sign. Factor the 7. And you'll have 7 times tan squared plus 1. But again, tan squared theta plus 1 is a secant squared. So under the radical sign, we're going to have a 7 secant squared of theta. Now I can take the square root of each term there, and I get a square root of 7 times the secant of theta. And so altogether, I'll get a 7 halves out front. And then the integral of secant cubed of theta. Now I need some help. We got a secant squared. Okay. Usually if we have a secant squared, we want a tangent in there, but I can't put a tangent in there for the secant. And I don't want to take out my secant squared, I just put it in there. So from here, I'm going to do integration by parts. One term I know how to integrate, one term I know how to differentiate. I know how to integrate secant squared, and I know how to differentiate secant. And the integration by parts right here. We'll take u to be secant theta, and dv to be the secant squared of theta. So the du, remember, oh, there it is over there, it's looking right at you. That's the log secant of theta plus the tangent of theta. Oh, sorry, that's not du, that's the integral. Root of secant is secant theta tan theta. Integral secant squared. Secant squared. Tangent. And so this integral becomes 7 halves times uv minus the integral of v du. So uv is secant theta tan theta minus the integral of v times du. Secant of theta, tan theta times another tan theta, will give me a tangent squared theta. Anybody here integrate secant times tangent squared of theta? Replace tangent squared with secant squared minus 1. It's done. Let's do it. Let's see. I'm going to go ahead and distribute the 7 halves. Replacing tangent squared theta with secant squared theta minus 1. So we could integrate secant cubed of theta. distribute that, it gives me plus 7 halves, the integral form in theta. Here we are back to where we started. This gives me a secant cube. This looks like a secant. Good though. Well, when you're integrating, the 7 halves secant cube. And then like 7 halves secant cube, what's in that type of 7 halves secant cube? What do we do? Add it. Put the two secant cube integrals together. This integral is over here. Okay? So I'm going to add that to that integral and get 14 halves secant cube theta. 14 halves is just 7. So I'll go ahead and write it as 14 halves so you see where I got it. So I've got, let me just call this integral I. That integral is over here. I'm going to add it over here. So we have 14 halves times I is equal to 7 halves secant theta tan theta plus the integral of this secant theta. That integral has just a natural law. So that's just a 7 over there. If I divide both sides by 7, or do I want to keep my 7 halves? I don't know how I want to do it. How do I want to do it? I'm solving for this one. So I'm going to go ahead and divide by 7 so that all of this, which was all of that, is equal to that integral. So if I divide by 7, that becomes a 1/2 and a 1/2. And so our original integral is equal to the secant of theta times the tangent of theta plus the natural log of secant of theta plus the tangent of theta. Both of those are multiplied by 1/2. So I'm just going to put them all over 2. Now let's do that step to get everything back in terms of x. And that comes from the original step, from here. 2x divided by the square root of 7 is equal to the tangent of theta. So in picture form, 2x is here, the square root of 7 is there. This squared plus that squared gives us the hypotenuse squared. So that should be the 4x plus 7, 4x squared plus 7, and then a radical sum. So the secant of that angle is the square root of 4x squared plus 7 over the square root of 7. The tangent we have 2x over the square root of 7. Fill them in and we're done. Secant was hypotenuse. Tangent is 2x over the square root of 7. And then the natural log of the secant plus the tangent. All of that divided by 2. And back on the plus sign. So look how innocent this integral looked when it came to our secant cube integral. That was one that we did the other day, and I said that was an integration by parts that goes circular. I even said if I had $1 each time I did integration by parts of secant cube, and I did $2. So there I did it again. Cha-ching. It looks like it should be a very easy integral that turns into a No. Got time for more. I bet you're glad. Okay, so this time I gave you a denominator that has a radical sign, but it has an x squared plus 4x plus 13 in it. So it's got a first degree term in it. And none of these plans have a first degree term in it. You make a quick check to see if it's a UDU integral, but it's not, because the derivative of x squared plus 4x plus 13 is 2x plus 4. I don't have a 2x plus 4 in here. So I don't have one of those, and I don't have a UDU. Yes, sir. Okay. Are there factors of 13 that add to 4?
No, I mean, it's not gonna be easy, but that might be easier.
Sure, it might be. It might be if we're lucky. Like what? Well, Kelly, Captain, factor to your heart's content. I got something that doesn't factor. We can try to complete the square. Maybe then that things will look better for us. Okay, so let's do that. Let's complete the square, because this involves differences or sums of perfect squares, and I don't have that here. So let's do the algebra and completing the square and see if that helps. The x squared plus 4x together, I'm going to add something here. I'm going to take it back out, and then I'm going to add the 13. The number that I add and take out has to be something that has two like factors that add to 4. I'm going to add a 4 right here. So the x squared plus 4x plus 4 is now a perfect square. X plus 2 all squared. The negative 4 plus 13 gives me a plus 9. So I've done this to the integral. Now, if I didn't have that square root sign, that's an inverse tangent integral. But I do have the square root sign. So we can't take the square root of each term in sum. So that's when we're kind of stuck. It's still not a UDU integral because there's an x squared here. There's not next to the first power up there. So what can we try? It looks most like this. It's got the plus sign. Let's take the x plus 2 and let it equal to 3 times the tangent of theta. Take this as in the parentheses, x plus 2, and say that that's equal to 3 times the tangent of theta. take the derivative of both sides. Derivative of x plus 2 gives me the dx. The derivative of 3 tan theta is 3 secant squared theta. Now substitute that in and see if our integral cleans up to something that we can do. Something we do earlier. Okay, so if x plus 2 is 3 tan theta, x plus 2 all squared will be 9 tangent squared theta. Can I see that? Now plus that 9, slap the radical sign back on it. And now dx is 3 secant squared theta d theta. What's going to happen to the 9 tan squared theta plus 9? All right, I'm going to get a 9 times secant squared because I factor out the 9. And there's my Pythagorean identity, tan squared theta plus 1. Tan squared theta plus 1 is secant squared. So that's what's under the square root sign. We take the square root of that now that we can, make this sum into a product. Now my denominator is just 3 secant theta. If that looks familiar, we did this integral not too long ago. That reduces just to the integral of the secant of theta. What memorize? Natural log of secant theta plus tangent theta. Now let's go back and do that in terms of the original variables. We're going to find it from the original substitution. Solve that equation for the tangent of theta. Tangent of theta will be x plus 2 divided by 3. I don't think there's a tangent. And in the picture, tangent again is opposite over adjacent. So this is x plus 2. This is the 3. Length squared plus length squared is hypotenuse squared. This is the x plus 2 all squared plus 9. You can multiply it after that, or you can leave it like that, and I'll just leave it like that. Secant is hypotenuse over adjacent. X plus 2 squared plus 9 over 3. Tangent we said was x plus 2 over 3 plus that secant. So if you've got an x to the first power term in it, then completing the square is typically something that will help us to get to where we can do a trig substitution. But it's the square root signs that typically give us trouble. And these things allow us to get rid of square root signs because our manipulations give us a perfect square down there. Okay. You probably want another one.
Which means better.
Yep. you got that look on your face, like. Is that from Dickens' novel, Lisa? Can I have some more? You don't want to like do your spring break study.
Yeah.
Maybe if not, we have online, it's not.
Or the day before we go.
Well, we can worry about that later. We'll probably need to tell you what snowflakes. I would ask the same thing. You want to try a test?
Wow. Yeah, it's not that long.
I understand. Okay, let's try it. Seems like we've done all of them now. I think I'll do one that I could do both ways, with algebra or with a trig sub. So why do I think that I could do this with either algebra or a trig substitution? Maybe see some algebra that we can do. Kinda. I know the derivative here is going to involve an x. So I can think of this x cubed as an x squared times an x. Okay? So watch the algebra. Let's do algebra first. I'm going to take u to be 9 minus x squared. Then du is going to be a minus 2x dx, where I'm going to fetch an x from here to be the du term. So negative 1/2 du is the x dx. So now I've got to say that I've got this expression. Right? So what am I going to do with that extra x squared on the top that so far is unaccounted for? See where I have the extra x squared? Ignore it, erase it, and go on without it. What do you want me to do with it? Yeah, I have some x squared in terms of u here. Swap places. X squared is 9 minus u. Now everything is accounted for. I have 9 minus u divided by the square root of u times a negative 1/2 du. Pretty easy. So I pull the 1/2 out. I divide each of these by the square root of u. Okay. So what made that happen was that I was able to do a double substitution to account for the extra x. We did almost the same problem with an x squared up here, and we didn't have that double substitution available. Maybe next to the 4th, that wouldn't be available either. Okay, I'm gonna get a -1/2, integrate here, add 1 to the half gives me a half. Divide by half puts a 2 up here. And then this is u to the 3/2 times the 2/3 here. And so I set my 1/2 through here. I get a -9 square root of 9 minus x squared. -1/2 gives me a plus 1/3. 9 minus x squared to the 3/2. That's kind of short. Let's see what it looks like if we try the trig substitution. How many of you would have thought of that, but I'm not suggesting. Not suggesting, it's in your bag of tricks. The bag of tricks is getting pretty dang heavy now. You got a lot of stuff in there. Or sometimes you pull something out and say, what's this for? All right, now let's try with our trig substitution. Let's do the same problem using our trig sub. It looks like this one. So we're going to take our x to be 3 sine of theta. Let's give it a shot. So, the trig sub. X is equal to 3 sine theta, so dx is 3 cosine theta d theta. So x cubed is going to be 3 sine of theta all cubed. So 3 cubed is 27. Sine cubed of theta. Down here I have 9 minus 9 sine squared of theta under the radical sign. And the dx is 3 cosine theta d theta. Nine minus 9 sine squared theta becomes 9 times 1 minus sine squared theta. And 1 minus sine squared is cosine squared. And so the square root of 9 cosine squared theta will give me a 3 cosine out there. So after I take the square root of it, it'll cancel with that term in front of the d theta. All you do is remember how to integrate sine cubed. Log power on. Log power was easy, guys. Pull out a sine and make it sine squared times sine. Sorry, 27 went right here. And sine squared is 1 minus cosine squared. So we'll take u to be cosine of theta. Du is minus the sine theta d theta. So I'll get minus sine with the du. So I get minus the integral 1 minus u squared du. When you integrate that, you get u minus u cubed over 3. When you distribute the minus sign, you get u cubed over 3 minus each u was the cosine of theta. And now, what am I going to do cosine of theta? Come over here. X over 3 is equal to the sine of theta. There's my theta. Sine is opposite over hypotenuse. There's the x. There's the 3. So I bet you $1 this is the 9 minus x squared. And then the cosine is the square root of 9 minus x squared over the hypotenuse is 3. I got to cube it and then divide it by 3. And over here, I just had it by itself. And that's kind of a radical version of the answer we had a minute ago when I had fractional exponents. But you get the same answer, just got to be what you think of. And I don't mind you doing it algebraically if you can think of it. And show all the steps in between. Yes, sir. Oh, yeah, there's a 27 out here somewhere. Keep losing the dang 27. And it's bad. Yeah? We spent a long time on this section, like 3 hours on this one section. We're getting the 5 hours today. You look like you've been here for 5 hours. Still like section 4. Section 4, we're going to do some integrals by partial fraction decomposition. I just said you're going to like it. You have between now and Wednesday to convince yourself to that.
Next exam.
Well, they're begging me to move it, so it might be coming up, isn't it? I don't know when it is. Am I supposed to know these things? Today is March 1st. Our next exam isn't scheduled until the 22nd.
I don't want to make it grade anything. Yeah, so here's my break. Cancel the test and move it.
Did everybody just live with the grade they got?
Just trust me,
You know what? That's like making a basketball team. Just practice, 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 and never have a game. I want you to have your final four.
That's all I'm saying. Fine, goodness.
All right, you guys at home doing okay? I'm gonna cut this off. Any questions, anybody? All right, I'm cutting you guys off. All good. Okay. Window.